Chapter 3 is all about applying the derivative, and we will get started by looking at what we call extrema on an interval of a function. You should have with you the exploration and class notes sheet for section 3.1, and we'll be using that very, very soon. As it says on the slide here, we're going to be looking at why a function that is continuous on a closed interval must have both a minimum and a maximum function value on that interval. And then we're going to be getting into the nuts and bolts of how do we determine those values analytically without needing a calculator or a graph. This will be more like when I was in high school and having to do things without graphing calculators. Of course, we already know what a continuous function is. When we talk about a closed interval, we are merely referring to an interval where the endpoints are included, right? So the way we write this, of course, would be in interval notation with the brackets, just like that. So let's move on to the exploration sheet where we can investigate this topic. We want to start by thinking about all the possible ways that a graph can have either a maximum or a minimum value. And I suggest one possible way is simply with a smooth curve that bottoms out like a parabola. So we might be talking about this, where that would be a minimum value. And of course, it has a complement of going like that, where you would have a maximum value of the smooth curve. But are there other ways that we can have maximums or minimums? I can think of basically two more ways that this could happen, two more basic ways. So give it some thought, pause the video, and see what you come up with. Well, hopefully you had some luck coming up with other ways that you can have maximums or minimums. One of the ways I was thinking about when I said there were two other ways to do it is, instead of having a nice smooth curve, of course, we could have a sudden abrupt change, right? Something like this. And hopefully remember what we call this. Of course, we can also have a minimum happening that way. Okay. Yeah, hopefully remember that we call this a cusp, right? So that's another way you can have a maximum or a minimum. There's still one third basic way that this can happen, and you have to be thinking like on an interval, okay, a closed interval, as we were talking about before. And so that would be, I don't know if anybody came up with this, but that would be if you had the endpoint of your interval be a maximum or a minimum. Okay, so we could have something like this. All right, you can see that would give us a maximum value and a minimum value for the function. Of course, keep in mind when we talk about function values, we're referring to the output values of the function, not the input values. So, typically it's your y value or, your output value. Now, I'm curious if anybody had any other ways of doing this. Perhaps you thought maybe something like this would give you a maximum or a minimum value, where instead of it being a closed interval, it might be an open interval. And there's a little problem with that, because if you're going to actually have a maximum value, you have to actually have a number. So, if we had a function like this, where, I'll go and draw an axis, and let's say that open unshaded circle is, say, at -3, okay? We couldn't say that -3 was the minimum value, because it doesn't actually equal -3. And there's really no single number we could say it is. I mean, you might think, well, maybe it's -2.99999. But no, maybe it goes even further. It goes to -2.9999999. Okay? So you can't really establish a single number when it's an unshaded circle or an open interval, and therefore we don't actually have a maximum or a minimum value when that happens. Of course, one other thought, perhaps you came up with would be, what if your function, just increases like that, with a vertical asymptote, or maybe even with a horizontal asymptote, maybe going something like this, all right? Well, first of all, we need to point out that we're not on a closed interval anymore, but also, we're certainly not reaching a maximum value, because there's no single number up here that we could say the function's going to equal. It just keeps going to infinity. And the same thing's kind of true on the minimum down here. We're not ever reaching a single number that we could pinpoint as being the minimum value. It's actually very similar to the unshaded circle situation where, you know, we're getting closer and closer and closer to some number but never actually reaching it. So these blue cases just don't work, and really the only three basic ways this can happen is either with a smooth curve, to have a cusp like this, sudden change, or to have some interval where the max or minimum happens at the endpoints. All right. So let's continue on down here now. What is true about the derivatives of the points where a maximum or minimum occurs for each of our examples? All right. Well, certainly, I think we're pretty familiar now that with one of these cases where we've got nice, smooth, rounded curve, our derivative is going to be 0, right? This is where the tangent line goes horizontal. So extrema occur when dy dx equals 0, okay? Or let's see, what's happening at a cusp? We've talked about that, right? The limit of your derivative from the left side of the curve is not matching the limit of the derivative from the right side. So when we have a cusp, and I even tested you this on Chapter 2's test, we have no derivative, right? So derivative is undefined. Okay, so let's fill that in. All right, or the other thing that can happen is we are at an endpoint. Okay, so we don't know really anything about the derivative there, but we're at an endpoint. In some ways, you could argue there is no derivative because we can't see what's coming from both sides of that point. We only have coming from one side. Okay, well let's move on into number 3, where we're going to define what we mean by extrema and also learn a new existence theorem. So when we want to refer to maxima and minima, that's the plural of course for maximum and minimum, when we want to refer to them in general, we talk about extrema. That is just the general word that encompasses both ideas, okay? And we're going to be taking a look at the fact that if we have a function that's continuous on some closed interval, there must contain extrema of both types, okay, max and min within that interval. We'll be looking at that in just a second. Let's make sure, first of all, we have a definition for extrema, or extreme values, another way you could refer to it. And I don't know if you want to write this definition down, but it should actually just make some good sense, and it's not something you're going to be tested on directly. But we should understand that, you know, some function value f of c is going to be a minimum of f on some interval I, as long as it is at least less than or equal to all the other output values for x in that interval I. And by the same token, f of c would be a maximum if it's greater than or equal to all the other values, f of x values in I. It shouldn't be too much of a leap to, you know, if you just want to play around and make some drawings, but, you know, if you sketch any kind of function, as long as you keep it continuous, there's got to be some maximum or minimum value on whatever closed interval you have, okay? There's no way around it. Now, if you don't have continuity, then you might end up with something else, and if you don't have a closed interval, you might end up with something else. But as long as you're including the endpoints of the interval and you've got continuity, you've got to have a single maximum value of that function as well as a single minimum value. And this is stated here in what we call the extreme value theorem. All right. If f is continuous on a closed interval from a to b, then f must have both a minimum value and a maximum value on the interval. Without even drawing axes, I'll just demonstrate with this little drawing, right? That looks like here we would have our maximum output value up here at the top of this curve, right? And our minimum value, let's see, we'll label that, it's a max. And our minimum value would be down here at the endpoint, okay? I did not have the space to include this theorem on the exploration sheet, so make sure that you have written this into your notes and that you have it. It is one of our 3 to 4 existence theorems that we're going to have this year, and you want to make sure it's in your notes. So going on down with number 3, let's take a look at parts A and B. I give you a graph here, and I want you to pause the video and answer these two questions by naming the maximum function value for f of x on our interval from A to B, and then also name the minimum function value for f of x. So pause and do that. Now, I'm not sure if you had a question about how do you answer this, like what kind of value you should be giving. You should be giving output values, right? Y values. Those are the function values. So name the maximum function value for f of x on this interval. We just need to find the highest value, and it looks like right up here we have our point, and straight across from it we can see that that has an output value of f of b. So f of b would be the answer, okay? Not b, but f of b. And then our minimum value looks like that's happening right down here at the point d, f of d. So f of d would be our minimum function value on this interval. Now, as we look at letter C in number 3, we can see here's another vocab word. Rather than just talking about extrema, we use this word relative extrema. Perhaps this is a word you heard back in pre-calculus. But I'm not going to actually define it for you right now, but just tell you that this function f of x that we were looking at has 2 relative extrema. It also has 2 absolute extrema. All right, and these two may coincide with the relative extrema. The absolute extrema are the ones you just found on the previous slide. Okay, so I'll give you that much. But see if you can also fill in where the relative extrema are. All right. It is possible, as it says, for relative minimum to also be an absolute minimum, so you could have some overlap there. All right. So identify each, both relative extrema and also both absolute extrema for f. All right. So let's see. Keeping in mind, we didn't define what relative extrema were. We're going to do that on the next slide, but I just thought maybe you've had some experience with it, or maybe you could just even figure out what's going to be the relative min and the relative max. Since there's only one of each on this graph, hopefully you kind of can see that maybe it might be f of a, that might be a relative min, or it might be f of d. Of course, we already said that f of d was the absolute minimum, so let's fill that in. Okay, whoops, f of d, and that happens at x equal to d, right? We also already said the absolute max was f of b, and that happens at x equal to b. All right. Now, it may be that the relative max and min are the same thing, but they're not. I'll tell you that right now. At least one of them's not. So, having said that, do you want to change your guesses for what the relative min and the relative max are? I'll let you do that right now if you want to pause the video. Okay, well, the relative min is actually the same as the absolute min. It is also f of d, okay, and it occurs at d. All right, the relative max, that would not be the same. That is not f of b at b. So if I say that, then probably you've already written down that it would be f of c at x equal to c. Yes, that is also a relative max. All right, so let's take a look at the definition of relative extrema and have that make sense with what we said on this graph. All right, so here are the definitions for relative extrema taken from page 165. As far as putting these in your notes, kind of like we were saying with just the definition of extrema, it's mainly something you just need to be able to recognize from a graph and understand its value. So I won't be quizzing you directly on this definition, but if you'd like to put it in your notes, it's fine. But it just says, of course, that as long as we have an open interval containing c, on which f of c is a maximum, then f of c is what we would call relative maximum of f. All right? And by the same token, if there's an open interval containing c, where f of c is a minimum, then f of c would be a relative minimum. So perhaps the tricky part might be this wording open interval as opposed to a closed interval. All right, and I do explain that the plural is going to be maxima and minima. F of c is a relative maximum. Certainly, we could come up with an open interval, okay, like maybe on this side, and we can see that f of c is the maximum value, all right? This open interval stuff is there so that we don't end up calling an endpoint the relative maximum or relative minimum, okay? You see, if you're thinking that, that f of b up here is a relative maximum, it's not. I mean, we can have an open interval coming from the left side, but if we're going to include that point, we don't have an open interval from the right side, okay? We don't have, we don't have it doing, doing something like this, and we have an open interval like that. So that open interval stipulation really is working to keep endpoints from being relative maxes and relative mids, all right? Doesn't have to be a smooth curve, okay, but it can be, like here we can have a cusp, but you do have to have points surrounding on both sides of a relative min or a relative max. That's the main thing to keep in mind. Okay, so let's move on to number 4. You'll have to turn the page. Perhaps in the back of your head you've kind of been thinking, I'm not sure Mr. Whipple has taken into account all the cases we could have. What if we had something like this, where it's just a horizontal line? How can you have both a minimum and a maximum value on this interval? Well, good thought. I'm glad you're thinking that way if that was in your head. However, we still do have both a maximum and a minimum value. They just happen to be the same number, right? The minimum value here is going to be 2, and the maximum value is also going to be 2. Okay? Keep in mind we are talking about output values, not the input values. All right, well now let's move on and compare the extreme value theorem to the other existence theorem that we've already learned. So the extreme value theorem is, of course, now our second existence theorem, and in both cases continuity guarantees something, right? So let's just review here. What did continuity guarantee back in chapter 1? Well, it guaranteed that as long as you have continuity on your closed interval here, then you could pick any output value between the output value of one endpoint and the output value of the other endpoint. You could choose any output value here. I chose K right here in the middle somewhere, but it could have been up here, it could have been down here. Choose any one of these output values, then the intermediate value theorem guarantees that there has to be some point in your interval that has that output value. So it basically states that there must be some number C in the interval from A to B, such that f of c, the output value at c, equals the output value that we chose, that number k. As long as you've got continuity, that has to be the case. And of course we talked about how the title of the theorem is nice because it tells you what what it guarantees. It guarantees you an intermediate value between your two endpoints. Well, we can say the same thing with the extreme value theorem. It's named very appropriately. What does it guarantee us? Two extreme values. It guarantees us an extreme low value, a minimum, and it guarantees us the maximum value. So it's appropriately named, and I think a lot of students feel like the extreme value theorem is even easier than the intermediate value theorem, because all you have to say is, as long as you've got continuity, you've got a maximum on the interval, and you've got a minimum on the interval. Okay, I had to squeeze this next slide in to get it to fit, but we're going to now be taking a look at how we can use calculus to help us find extrema on a closed interval. We're interested in finding both the maximum on the interval as well as the minimum. And when I say maximum and minimum, I'm referring to the absolute maximum and the absolute minimum. We're not concerning ourselves in this section with relative extrema. We'll do that in a future section in this chapter. All right, so here are the steps. First of all, you need to determine what are called critical numbers for f in the open interval from A to B. All right, and I'm defining what a critical number is. This is kind of an important term because it is used even by the AP people. All right, it is defined on page 166. It's any number c in your interval for which the derivative at c is either 0 or is undefined. So when we talk about a critical number, we're talking about an input value, okay, where your derivative is 0 or undefined. Now, relative extrema may not occur at a particular critical number as we see over here in the graph, okay? But you need to keep in mind that you cannot have a relative max or min without it occurring at a critical number. So that's why we need to find them. It's possible we could have our max or min at any of the critical numbers, so we need to make sure we check all of them. That's why we have to determine all critical numbers for f. So let's take a look. We can see here it is possible, like look at letter C, that you could have your derivative be 0 and not have a minimum or a maximum there. Okay, it just goes horizontal. You have to remember that's all a derivative value of 0 means, is that the graph goes horizontal. We can see here at letter D, we might have a case where the graph goes vertical, and when that happens, yeah, we don't have a maximum or a minimum necessarily. Okay, and of course when a graph goes vertical, that's where you have an undefined slope, right? Vertical means that your slope is undefined. All right, and then of course there's also at letter E, we have an undefined derivative here, and there's no minimum or maximum. This of course would be where we have like a vertical asymptote. Where we lack continuity, we're not going to have a max or a min. But still, we need to check all the critical numbers because it's likely we could have a max or min at one of them. All right, so once you've located your critical numbers, then all you have to do is plug those critical numbers into f and determine what the output values are at each critical number. And then one more step, you want to determine what the output values are at each of the endpoints. So you have to determine f of a and f of b. So once you have all the output values at your critical numbers and all the output values at your endpoints, then you just compare them, okay? And whichever is the lowest of those output values, that's the absolute minimum on your interval. And whichever one's the highest, that's your absolute max. That's all there is to it. You might be scratching your head and you say, are you sure we won't have missed something if we do this? But remember all the examples we've done earlier in this video. Every time we had a relative max or a relative min, either the derivative had to be 0 or had to be undefined, like at a cusp, or your max or min happened at the endpoint, okay? That's the only basically the only three ways that you can have a maximum or a minimum. So that's why we check those critical numbers, and we also check the endpoints. You have to make sure you check the endpoints, though, otherwise you might miss something. So let's go down to number 7, where we'll do an actual example similar to what you might do on the homework. Keep in mind now the idea is to do this problem without a calculator, without looking at a graph. We're just going to try to determine the absolute extrema on the interval from -1 to 2, all right, for our function here. And we're just going to follow those steps that we were just looking at. You have those steps right in front of you, and I'll be referring to them as we go. Let's just go ahead and label this for step A. We need to determine all the critical numbers. All right, I'll just write that. Determine all critical values. Keep in mind those are input values, okay? All critical numbers, and we do need the derivative to do that, right? We're looking for where the derivative is either 0 or undefined. So why don't you pause and get your derivative for f and check it with what I do. Okay, so this function is not too hard to get the derivative of. We just need to use our power function. But perhaps maybe you didn't write it this way down here. Once I'd used my power function and got my exponent, I'm going to go ahead now and change it back so that it's got the cube root in it, which is the -1/3. And I also went ahead and wrote it without the negative exponent. This will actually be helpful because now we're moving further. Back in chapter 2, you were just trying to find the derivative. Now we're actually having to do something with the derivative. And what we're doing is two things. First of all, we need to check and see, is there anywhere where the derivative is undefined? And I think we can see that we've got a little danger point right here, right? We do have a denominator. Okay, our root is okay because it's an odd root. We don't have to worry about that. But we do have to worry about our denominator. We don't want that to equal 0. So we'll make a note that first of all, f prime, okay, is undefined, all right, at x equal to 0. That's important because that means 0 is a critical number. All right, we could have a cusp there. That's why we're checking on that. And to make my point here, if I had not rewritten this so that I didn't have a negative exponent, I might not have realized that was a danger point and that we would have an undefined derivative there. So that's a reason to do that. Okay, now we need to go further also. Remember, a critical number is also where your derivative equals 0. So we're going to set 0 equal to 1 minus 2 over 3 times the cube root of x. All right? I'd like you to pause the video right now and solve this equation for x. See if you get what I got. All right, so did you get 8 over 27? Maybe you did, maybe you didn't. Let's look and see how I got 8 over 27. All right, I just, of course, went ahead and added this fraction all the way over here, so now I'm just dealing with positive values. I had to get rid of my 2 on top and my 3 on the bottom, so I simply multiplied both sides by 3 halves, right? That would cancel out the 2 on top, and it'll cancel out the 3 on the bottom, and 1 times 3 halves just gives me 3 halves. And now I've got 1 over the cube root of x is equal to 3 halves. I would like to not be dealing with that fraction and just flip it, so that's what I did. I just flipped both sides. As long as you do the same thing to both sides, you're good. So that would mean the cube root of x has to equal 2/3, and to get rid of the cube root, of course, I need to cube both sides, so I got x equals 8 over 27. So we can see that we actually have 2 critical numbers here. We have the one critical number at x equal to 0, and we have our other critical number down here at 8 over 27. And you might have seen this little chart over here and wonder what it was all about. Well, we're going to use this now a little bit, because now that we know what our critical numbers are, we're going to fill them in over here. All right, so I'm going to fill in, let's see, I got 0 is right here. I'm going to put 8 over 27 right here. Okay, and step B said we need to determine what the output values are for our critical numbers. All right, and that goes all the way back to f of x. Looks like I've lost my function f of x, so let me write it back up here. It was f of x, whoops, f of x is equal to x minus x to the 2/3, I believe, right? Yes, 2/3. Okay, so let's see if we can figure out what f of 0 is and f of 8 over 27 is. Okay, so I've got, that's what this this line right up here is for. Okay, so f of 0, of course, is very quickly is just going to be 0, which is nice. And then f of 8 over 27, all right, we would have, let's see, we're going to have to figure this out. We got 8 over 27 minus let's see, it's the cube roots of 8 over 27 squared. Okay, let's do the root first. That's easy enough, and then we'll square it. Okay, if you write it that way, it's doable, because cube root's just going to be, what, 2/3, and then when we're squaring 2/3, we'd get 4/9. So it's 8 over 27 minus 4/9. If we get a common denominator, we have 8 over 27 minus, let's see, 9 goes in 27 3 times, so 12 over 27. So it looks like we get negative 4 over 27. All right? Okay. Now you might say, well, there's our maximum value and our minimum value, but hold on there. We still have not checked the endpoints, so we need to also plug in -1, and we also need to plug in 2. Okay? And -1, let's see if we plug that in, we'll just have -1 minus, and when we square the -1, we'll have a positive 1. So it's -1 minus 1, so we'll actually get -2 back when we plug in the -1. And now if we plug in 2, this is the hard one. Since we don't have our calculators, we just got to think. Here, I'm going to do this in red just real quickly. So we have 2 minus, let's see, the cube root of 2, okay, and then we have to square it. All right, well, the cube root of 2, let's see, the square root of 2 is about 1.4. The cube root of 2, it's a little smaller, but it's not as small as 1, okay? And then we're going to square it. So we have a number a little bit bigger than 1 that we're then going to square. If you think about it, the square of this number is going to be something a little bit smaller than 2. because you know, the way we get 2 by squaring is by squaring the square root of 2, which is 1.4. Well, cube root is a little bit smaller than that, so when we square the cube root of 2, we won't get 2. I mean, we'll get something a little smaller. So we know that 2 minus this number is at least greater than 0. It's at least a positive number. And given that, that means it's got to be the maximum, right? It's got to be bigger than 0, and it's got to be bigger than the 2 negative numbers. So we're just going to go with this. I'll tell you right now, if you were to plug it in your calculator, it would come out to be about 0.413. That's kind of cheating, but at least we argue that it is a positive number, which means it's got to be the max. All right. So all we have to do now is state our answers. All right. So I've written my answers down here. Notice I did not write the x values. Okay. The question didn't ask for them. The question said determine the absolute extrema, and what that means is the output values, or the f of x values. So that's why we're giving y values. Now, if you wanted to say that the absolute max is 0.413 and then write at x equal to 2, that would be fine. And then for the absolute min, say that's at x equal to -1. No problem with that, but make sure that you are stating very clearly that the maximum value is the output value and the absolute minimum value is the other output value. Okay, so we see with this example that we ended up with our extrema at the endpoints of the closed interval. Let's take a quick look at the graph. You can just put your calculator out, open a graphs page, and plug the formula in, and let's see if this makes some sense. I've got the graph on the next slide here. Here's our graph. You can see my window. I've zoomed in a little bit, so I'm going from -1.7 to a 2.6 on the x's, and only from -1.6 all the way up to 0.8 on the y's. But this gives us a good view of what's going on here, and it should kind of corroborate all the analysis we just did. We can see, let's see, we're not even, well, let's see, we're going out to -1. If I can find where -1 is, these are tenths, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's about -1 right out here, -1. And so the y value is somewhere down here below, and it would be at -2. Definitely the minimum on this interval. 2 is, let's see, 0.6, 0.5, 4, 3, 2, 1. 2 is somewhere about right here, okay? And right up there, maybe I should be using red since everything else is red. And that was our maximum value at about 0.413. So we can see that it does appear that our endpoints are where the max and the min are. But we can also see, how our analysis makes sense with the other points, right? We can definitely see there is a cusp at 0. That's where we found the derivative to be undefined. And we can also see somewhere right in here, we have our derivative equaling 0. Well, that must be the 8/27, and I invite you, if you want to, check that out with the calculator. If you go to the menu button and then choose, I believe it's Analyze Graph, and from there you should see minimum and maximum options, so you can try the minimum and see if it doesn't give you back 8/27. Of course, it'll give it to you in decimal form, but you can check that out. Okay, well, this is all I got on this video. Hopefully it's not too long, but it'll be good that you're doing the problems in class, and if you run into any situations, do ask. We can talk about them, and it wouldn't be a bad idea if you want to go ahead and get started on a couple if you have the time. See you in class.